Double descent and over-parameterized models, from global feature selection to context-aware learning. Hello, my name is Chong-Ho Alex Yu. I am a professor of artificial intelligence and data science. In this presentation, I will go over how the rapid expansion of computational power and ecosystems, such as GPU and cloud computing, the advent of foundational artificial intelligence models, such as ChatGPT and Claude, and the availability of big data have precipitated a radical paradigm shift. This shift challenges the conventional notions of Occam's razor and the bias-variance trade-off. The catalyst for this transformation is the empirical discovery of the double descent phenomenon. Contrary to classical expectations, modern deep learning models, which are often over-parameterized to the point of containing far more parameters than training samples, do not necessarily exhibit increased test error as complexity grows. Instead, as model capacity passes the interpolation threshold, the test risk frequently begins to decrease again, often reaching levels of accuracy that surpass those of their simpler, under-parameterized predecessors. This discovery reveals that over-parameterized models are capable of finding stable, highly accurate solutions in high-dimensional spaces that classical statistics once deemed unlearnable due to the curse of dimensionality. Recent empirical evidence from deep learning practice has shattered this classical dogma. Modern neural networks, often possessing millions or billions of parameters, frequently interpolate noisy training data, yet achieve state-of-the-art generalization performance. As model complexity is increased far beyond the interpolation threshold, the test error begins to descend a second time. This double descent curve subsumes the classical U-shaped curve, extending it into a new regime where over-parameterization provides a surprising benefit. To understand how double descent works, it is essential to discuss the difference between conventional gradient descent, GD, and stochastic gradient descent, SGD. Gradient descent and stochastic gradient descent both seek to reduce a model's loss by moving parameters in the direction that improves prediction, but they differ in how each update is computed. GD uses the entire training dataset to calculate each update, making its path more stable and deterministic, but often slower and computationally expensive for large datasets. SGD, by contrast, updates the model using one example or a small mini-batch at a time, producing a noisier path, but allowing much faster and more scalable learning. This difference matters because the stochasticity of SGD is not merely a computational shortcut. In complex models, it can influence which of the many possible solutions the optimizer reaches. This optimization behavior should not, however, be conflated with the cause of double descent. Specifically, the mechanism underlying the second descent is attributed to the implicit bias of the learning procedure, rather than to stochastic noise as such. The phenomenon is observed even with full batch gradient descent and in closed form minimum norm solutions to linear and random feature models, which indicates that over-parameterization together with implicit regularization, not the stochasticity of SGD, is the essential ingredient. When a model is highly over-parameterized, there are infinitely many functions that can interpolate the training data. In this high-dimensional landscape, the optimization process naturally gravitates toward the smoothest or minimal norm function compatible with the data. This preference for regularity acts as a powerful form of implicit regularization, allowing the model to find a solution that is simple in terms of its function space norm, even if it is complex in terms of its parameter count. In the over-parameterized regime, both the bias and the variance can decrease as the number of parameters increases. Specifically, the variance diverges at the interpolation threshold, but then declines as the model becomes more over-parameterized, often falling below the level observed in the classical optimal parsimonious model. This realization suggests that the simplicity sought by Occam's razor may not reside in the number of variables or parameters, but in the smoothness of the high-dimensional representation learned by the model. These results, however, should not be read as a universal law. Double descent is an empirical phenomenon observed most robustly in very large, over-parameterized deep networks trained on large datasets. and its appearance is conditional. The model must be expressive enough to pass well beyond the interpolation threshold. The benefit is sensitive to the level of label noise, and it can be substantially weakened or removed by appropriate regularization. Crucially, the data regime typical of a single institution, modest sample sizes, heterogeneous and noisy tabular features, and many uninformative variables is not the regime in which a second descent is reliably observed. On precisely this kind of tabular data, well-regularized tree ensembles such as gradient-boosted trees frequently match or outperform deep networks, and classical overfitting concerns continue to apply. The implication for researchers and data analysts is therefore conditional rather than guaranteed. Double descent shows that complexity is not inherently harmful and that high-capacity, representation-rich models are worth considering, but it does not warrant assuming that a larger model will generalize better on any given dataset. Whether the over-parameterized regime confers an advantage in a particular setting is an empirical question to be tested, not a property to be presumed. The shift from the parsimony-centric regime to the over-parameterized regime has fundamental implications for how features are handled in predictive models. The traditional approach relied on global feature selection, which assumes that a fixed, small subset of variables is sufficient to represent the entire population. In contrast, the contextual attention regime, powered by transformer architectures, allows models to dynamically prioritize different features for each individual instance. Traditional feature selection methods, such as L1 or L2 regularization, lasso, ridge, and elastic net in generalized regression, or filter methods based on mutual information, perform a global analysis to rank and select features. The resulting model uses the same weights for the same features across all predictions. While this approach is computationally efficient and interpretable, it often fails when the relevance of a feature depends on the specific context of the subject. Context-aware models instead weigh the available inputs differently depending on the current case. For example, in a medical context, a model might give greater weight to blood pressure data for one patient, while drawing more on genetic markers or lifestyle history for another, depending on their individual health trajectory. Attention-based neural networks are well suited to this. For each input token, they compute weights over the other tokens in the sequence and form an input-dependent weighted combination of their representations. This is a soft, continuous reweighting rather than a discrete selection of features. Describing it as feature selection is therefore a useful analogy rather than a literal account of the mechanism. The preceding discussion of over-parameterized models and context-aware solutions may sound compelling in theory, but how well do these approaches work in practice? Stay tuned as we take a closer look at real-world applications of over-parameterized models. See you in the next video.